Section 3 of Chapter 15 deals with systems containing multiple equilibria. There are no new concepts here, just the application of all the things we've learned about equilibrium to systems containing multiple components. As previously mentioned, in any system, all equilibrium expressions must be simultaneously satisfied. This means that any equilibrium expression that you can write for any of the species in the solution must be true. As a somewhat simple example, consider a solution of 0.1 molar ammonia. What species are present in this solution? Obviously ammonia and water, but we know that ammonia is a weak base, so it will produce some hydroxide ions and ammonium ions. And in any aqueous solution, there will always be some hydronium ions as well. What equilibrium reactions can we write? We can write the reaction of ammonia in water, acting as a weak base to form the ammonium ion and hydroxide ions. This equilibrium will be governed by the Kb for ammonia. We know that any solution of water, that the concentration of hydroxide ions times the concentration of hydronium ions must be equal to 10 to the minus 14, according to the Kw. And we could also write a reaction of the ammonium ion reacting with water to make H plus and ammonia. This equilibrium would be governed by the Ka for the ammonium ion. If we use an ice table to represent the solution of 0.1 molar ammonia, if we show the ammonia reacting with water as a base to form ammonium ion and hydroxide, and set up the ice table, plug the values into the Kb expression, we get a value of x of 1.35 times 10 to the minus 3, which would be the concentration of the hydroxide ions as well as the ammonium ions. We could solve for the concentration of ammonia as 0.1 minus x, and we would get 0.0986 molar. On the other hand, if we look at the equilibrium expression for the ammonium ion and the Ka reaction, if we plug in our value of ammonium that we solved previously and ammonia 0.0986, plug this into the Ka expression, we would find that x is 7.67 times 10 to the minus 12, which would be equal to the concentration of the hydronium ion. Finally, if we look at the water equilibrium and plug in the values for hydroxide and hydronium ion that we previously obtained, we see that it does in fact equal the Kw value. Solving for the concentrations of all the species, we see that everything is self-consistent. In other words, all three of those expressions were simultaneously satisfied by one set of concentrations. When dealing with a system containing multiple components, it's useful to write down the major species and then look for reactions that may occur between the species. If we only need to know qualitatively what happens, we can generally use Le Chatelier's principle. If we want to calculate concentrations, we have to use equilibrium expressions and ice tables. Let's start with a qualitative example. Nickel 2 carbonate is a sparingly soluble solid. How will the amount of solid nickel 2 carbonate change when the following are added to a system containing nickel 2 carbonate solid in equilibrium with an aqueous solution of its ions. How will the concentrations of the nickel 2 plus and carbonate ions change with these additions? Whenever I see a word problem, I like to try to draw a picture if I can to help me figure out what is going on. Here we're told that we have a solution containing nickel ions and carbonate ions in equilibrium with solid nickel 2 carbonate. We can write a reaction showing this equilibrium. The KSP would be the product concentrations of the nickel 2 plus ion and the carbonate ion. In this system, since we have some solid present in equilibrium with its ions, the solution is considered to be saturated. What happens when we add some nickel 2 nitrate solid? Nickel 2 nitrate is soluble, so adding nickel 2 nitrate solid will increase the concentration of nickel ions in the solution. This will cause a backward shift towards reactants according to Le Chatelier's principle. This means that more nickel 2 carbonate solid will form. The concentration of nickel ions is increased by the addition, but the concentration of carbonate ions is actually decreased by the backward shift in the reaction. Remember that the value of KSP is a constant, so if the concentration of nickel ions increases, the concentration of carbonate ions has to decrease to maintain equilibrium. What if we add potassium perchlorate? Neither potassium ions nor perchlorate ions participate in the above equilibrium, and neither of these ions react with any of the components above. So the addition of potassium perchlorate has no effect on the position of equilibrium and no effect on the concentrations of ions in solution. What about adding some more nickel 2 carbonate solid? The addition of nickel 2 carbonate solid will not affect the position of equilibrium because solids don't appear in the equilibrium expression. Obviously, the amount of solid is increased by the addition, but since there is no shift in the position of equilibrium, the concentrations of the ions remain unchanged. What about adding potassium carbonate? Addition of potassium carbonate adds carbonate ions to the solution. This is similar to the situation in where a product was added. So the reaction will shift backwards towards reactants, forming more solid and reducing the concentration of nickel ions in solution. What if we add some nitric acid? Addition of nitric acid causes a reduction in the amount of solid because the acid reacts with the basic carbonate ions. This removes one of the products, causing a shift according to Le Chatelier's principle towards products. This will decrease the amount of solid present. The concentration of nickel ions in solution will increase by the dissolution reaction, but the concentration of carbonate ions will decrease because they are being removed by reaction with nitric acid. When you have multiple equilibria present and you want to quantify the amounts of all the species, follow the steps that we use for buffer and titration calculations. Namely, first draw a picture if you can, identify the major species, look for reactions between any of the species present, and identify these reactions as involving strong species, in which case we'll use stoichiometry, or weak acids or bases, for which we'll use equilibria calculations. Always do the strong reactions first using stoichiometry, then write equilibrium expressions for all relevant equilibrium. Start with those that have the largest K values or the highest concentrations. Remember that all equations must be simultaneously satisfied. Let's now apply these steps to a quantitative example. What mass of ammonia would be required to prepare 1 liter of a solution that will dissolve 2 grams of silver chloride solid by the formation of the silver ammonia complex? Let's start by drawing a picture and identifying the major species present. The problem indicates that at the end, we want all of the silver chloride to be dissolved. What reaction will dissolve the silver chloride solid? Ammonia is a good complexing agent and can react with silver ions to form a complex ion. If we combine this complex ion formation reaction with the KSP expression for silver chloride, we get an overall reaction that shows the dissolution of silver chloride solid to form the silver ammonia complex ion. At the end of our problem, the solution should look like this, where all of the silver chloride solid has been dissolved and we have the following ions in solution. So starting with the reaction from the previous slide, showing the dissolution of the silver chloride solid with ammonia to form the complex ion, we can set up an ice table to calculate the quantities in the system. We're looking for how much ammonia we'll need to add to get all of the silver chloride to dissolve. Since we don't know that, let's put a question mark in there. We'll assume that we start with 0 molar of the two products. Our change row is always plus and minus x's based on stoichiometry. We're looking for how much ammonia to add to get all of the silver chloride to dissolve. If all of the silver chloride dissolves, what would be the final concentrations that would be produced of the chloride ion and the silver complex? We were told that we started with 2 grams of silver chloride. We can use the molar mass of silver chloride to convert this to moles, and we see from the balanced chemical equation above that 1 mole of the silver complex ion is formed per mole of silver chloride. We were told that we're going to have 1 liter total of solution, so this gives us that at the end, if everything is dissolved, we should have 0.01395 molar of the complex ion. We can do a similar equation to show the concentration of chloride ion. Notice that since equal moles of the silver complex and chloride are produced in the above reaction, we should get the same result. And in fact, we do. We can put these values into the equilibrium row of our table. What about the final concentration of ammonia? We need the equilibrium expression to be satisfied. So we can use that expression to solve for the concentration of ammonia that would be in equilibrium with these concentrations of silver complex and chloride. We had a K value of the above reaction of 2.7 times 10 to the minus 3, and our equilibrium expression is product concentrations over reactant concentrations. Notice that the ammonia concentration is squared due to the 2 coefficient. Solving this for ammonia concentration and plugging in the values from the table, we see that the ammonia concentration needs to be 0.268 molar at equilibrium. What about the initial concentration of ammonia? Since we want the final concentration to be 0.268 molar, and the equilibrium rho should be question mark minus 2x is equal to 0.268, and we know the value of x is 0.01395, we find that the initial concentration of ammonia is going to have to be 0.296 molar. The question asks for how many grams of ammonia must be added. So since the volume of the solution is 1 liter, we take the concentration times the 1 liter times the molar mass of ammonia and find that we need to add 5.04 grams of ammonia to completely dissolve the 2 grams of silver chloride. In this presentation, we've solved a fairly complicated equilibrium problem by taking it a step at a time. Now pause the presentation and try group problem number 10 from the yellow packet on your own to see if you've understood. The answer will be given on the next slide. Hopefully you were able to determine the answer to be 1.30 grams of potassium cyanide.